Okay, let's continue with solving the problem of vibrating string. So what we did was we found out what is the equation describing the vibration of the string. So the equation we got at the end was the second derivative of u with respect to x is equal to 1 over some constant c squared. Second derivative of u with respect to t, where x is bounded by 0 and a, and t is positive. We start at sometime t equals 0. We have some boundary value conditions. U at the point 0 at any time t is given, it's 0. U at the other boundary a at the any time t is also equal to 0. In other words, we have fixed these two endpoints of the string, and the string is vibrating there. We have initial conditions, so u of x at time 0 is given by f of x, and derivative of u with respect to time at the point x at time t equals 0 is given by another function g of x. These are the things we know and we want to solve it. So the idea is very similar to what we did before. We start by using the product method. So similar to what we did for the heat equation, I would assume that u of x and t can be written as product of two functions, where one is only a function of x. I would show that with f of x. The other one is only a function of time. We show that with t of t time. Now let's plug that into our equation. Let's plug this definition of u into this equation we have here. So the second derivative of u with respect to x. So rather than u here, we have f of x, t of t. Well, the second part is independent of x, so the derivative only applies to the first function. So we get the second derivative of f with respect to x times t of t. That would be the left-hand side of the equation. What is the right-hand side? The right-hand side is equal to 1 over c squared, second derivative of u with respect to time. What is derivative of u with respect to time? Well, again, if we write down what we have for u, which is f of x t of t, the derivative with respect to time only acts on the function t. It doesn't do anything with function f because it's not a function of t. It's like a constant, or in other words, derivative of f with respect to t is 0. So we would have f of x over c squared, second derivative of t with respect to t. Now the left-hand side and right-hand side should be equal. So what we have here should be equal to what we have here. So let's write down that equation. Second derivative of f with respect to x times t is equal to 1 over c squared f. Oh, we know what is it. Second derivative of t with respect to t. This is what we would get, right? Now we do exactly what we did before. We would separate the variables. Separation of variables. So we have the second derivative of f with respect to x over f is equal to 1 over c squared. Second derivative of t with respect to t over t. Same type of argument we did for heat equation works here. This is function of x. This is function of t. They can't be equal unless there is no x in the first fraction, no t in the second fraction. In other words, if they are equal to a constant. Now, completely similar to the analysis we did before here, we understand this constant should be negative. And therefore, we can denote that with minus something squared, minus lambda squared. Again, it's very similar to what we had before. The difference is here, the equations we get here are different. So one of them is similar to what we had before. So if we show the second derivative of f with just f double prime and the second derivative of t with t double prime for simplicity, we get two equations. F double prime plus lambda squared f is equal to 0. T double prime plus c squared lambda squared t is equal to 0. So the equation for f is similar to what we had before. The equation for t is new. It's not similar to the equation for t which we had before. So we have these two equations. What about boundary value conditions? So boundary value conditions told us that u at x equal to 0 at any time t is equal to 0, u at a at any time t is equal to 0. Now, knowing that u is equal to f of x t of t, this means f of 0 t of t is equal to 0. Because we don't want t to be always 0. If t is always 0, u would always be 0. It forces us to assume that f of 0 is 0. On the other hand, because u of a and t is equal to 0, it implies f of a, t of t is equal to 0. And again, it implies f of a is equal to 0. So these are the boundary value conditions for the function f. We solved this equation with this boundary value condition. So if you remember, we solved this equation with exactly same boundary value condition. We learned lambda can be infinitely many different things. The eigenvalue can be n pi over a for any natural number n. And corresponding to lambda n, we had a solution fn, which, if you remember, it was sine of lambda nx, which is n pi over ax. So that's one part. What about the other part? Let's look at the other equation. So keep this thing here. We have, in some sense, half of the solution. We know what f is. Let's look and try to find what t is. T satisfies this condition. Right? So the characteristic equation is m squared plus c squared lambda squared is equal to 0. Therefore, m would be equal to plus minus I, imaginary number, c lambda. Therefore, the solutions to this equation would be cosine of c lambda and c lambda t, sorry, and sine of c lambda t. However, as we did in the previous part, there is not just one lambda, we have a sequence of lambda n equal to n pi over a. So for each lambda n, we get one of these. I would show that with c lambda n t, right? And the solution would be a linear combination of these things. So it would be, say, an times cosine of c lambda nt plus bn sine of c lambda nt. Because this solution depends on n, we are numerating them, I would denote that with Tn. So for any n, we have Fn, which is a solution for that lambda n, which was sine of lambda nx, and we have Tn, which is what we have here. So another point here is that the equation itself doesn't tell us anything about an and bn. We should use the initial condition to find them. We are going to do that. Any question up to this point in finding f and finding t, fn and tn? It's very similar to the things we did before. Okay, so ft would be a solution for the equation for u, but because f depends on n, t depends on n, for each n we have one solution, we denote that solution with un. So for any n, we get one solution for the wave equation. So this is equal to, well, fn was equal to sine of lambda nx, tn was equal to an cosine of lambda n ct plus bn sine of lambda n ct. So this is one solution for the wave equation. So in general, the general solution would be a linear combination of these. So the general solution would be a linear combination of these things. Note that for this linear combination, there is no reason to add extra coefficients here because this coefficient can be absorbed into an and bn. So there is really no need to add extra coefficients here. Now, the only things which I don't know in this solution are an and bn. We need to find an and bn. So our question is, what is an and what is bn? And the way to answer that question is by looking at the initial condition, right? That's how we can answer these type of questions. What was the initial condition? The initial condition told us that u at the time 0 is given and it's equal to f of x. So the initial condition told us u at x and 0 is equal to f of x. On the other hand, I can compute u at the time 0 by just inserting t equals 0 in this equation. So if t is equal to 0, this would be 0, therefore the sine is 0. And if t is 0, cosine would be 1, right? So if we let t to be equal to 0, what we are going to get is sigma, and goes from 1 to infinity. We have an times 1 times this coefficient here, sine of lambda nx, plus bn times 0, which is 0. Okay, we should use this equality to find an. We should use this to find a. We have done this thing a few times. I'm going to repeat that. So let's write down this equation. So we have the function f of x, which, remember, it is given, is equal to this infinite sum. The sum where n goes from 1 to infinity, an. All of these numbers an are unknown. We want to solve this equation to find them. Sine of lambda n x. Also remember that lambda n was equal to n pi over a. So for each n, I'm looking for an. So for example, if n shows this numerator, which goes from 1 to infinity, suppose I'm looking for one specific AM, where M can be any of them. In order to find that, what is that number, I would multiply both sides by sine of lambda mx. So fx times sine of lambda mx would be equal to sigma n goes from 1 to infinity a n sine of lambda nx times sine of lambda mx, right? Now the second step would be to integrate both sides with respect to x, right? I'm going to integrate both sides of this equation with respect to x, say from 0 to a. So I would have integral from 0 to a fx sine of lambda mx is equal to sigma m goes from 1 to infinity, a n is a constant, comes out, integral of sine of lambda nx sine of lambda mx dx from 0 to a. Now, remembering that lambda n is n pi over a, this thing here would be 0 if n is not equal to m, right? If they are equal to each other, this would be equal to 2 over a. So the right-hand side, the infinite sum on the right-hand side is always 0 unless n and m are equal. So all the terms in this infinite sum are equal to 0, but one of them. And that one is a m times 2 times 2 over, sorry, it would be a over 2. Why am I saying 2 over? It would be a over 2 times a over 2. So we can use to see what the value of am is for any m. So am is equal to 2 over a integral from 0 to a fx sine of lambda mx dx. So that would be the value of am for any m. For all natural numbers m, we have am. Is there any question from this computation? Is it clear for everyone? Okay, great. So going back to this thing we had here, now we know what an is, right? We found an. Now the only thing we don't know is bn. We need to try to find what bn is. We can find bn with the other boundary condition we had. Okay, so remember, we had another boundary condition. We can actually use the initial condition. So let's see. Yeah, sorry, the other initial condition. What does the other initial condition tell us? The other initial condition we had was the function describing derivative of u with respect to t at the time t equals 0. So we were assuming this is equal to g of x for some given function g, right? Now, on the other hand, u of x and t, we have an expression for that, right? U of x and t is equal to the sum, the infinite sum, and goes from 1 to infinity, sine of lambda nx times an cosine of lambda n ct plus bn sine of lambda n ct. Great. Now we can take derivative from this thing. Again, this is something we discussed a few times. Here we're assuming that we can take term by term derivative with respect to t. We can change the place of derivative with the infinite sum. This is part of our assumption, and we talked a few times about why it makes sense here to have this assumption. So sine of lambda n x would be like a constant for t. We should take derivative of cosine of lambda n ct and sine of lambda n ct. So we would get minus an lambda n c sine of lambda n ct plus bn lambda n c cosine of lambda n ct. That would be the result of our derivative. Now let t to be equal to 0. We would have derivative of u with respect to t at time t equal to 0. What is it going to be? Well, if t is 0, this term sine of t would also be 0. If t is equal to 0, cosine of 0 would be equal to 1. And therefore, the result is this is equal to sigma n goes from 1 to infinity sine of lambda n x times some constants, bn lambda n c. And we want to solve this equation for each bn. We want to find these numbers bn. So can we kind of get what bn is from this equation? Yes, we can. So see, this other initial condition told us u has this initial property that its derivative with respect to t at the time t equals 0 is equal to g. So what we have here should be equal to g of x. And we should, g of x is given. It's something we know what it is. So we should solve this equation for each bn. So we just write this here again, sigma n goes from 1 to infinity bn lambda n c times sine of lambda n x is equal to gx. And the question is, what is bn for each n? Okay, again, similar to what we did before, in order to find, so for some given m, natural number m, in order to find bm, what we can do is we can multiply both sides of this equation by sine of lambda mx, take integral just as we did before, and then we can get what bm is. So if we do exactly what we did for an, we would get the result for bn. Do we have, yeah, so it's going to be, let's see, we would take integral from 0 to a of gx sine of lambda m x, and then, sorry, what did we have here? 2 over a. So there we are going to have 2 over probably ac, if I, let's see, 2 over ac, yeah. If I remember correctly. Did we, let's go back here for a second. Let's make sure the computation for am was correct. So here we have that. Oh, we have lambda and 2. Sorry, I should correct this thing. So let's do the computation. I can't remember what was the value. Let's do it. So in order to find bm, I should multiply everything by sine of lambda mx. So gx sine of lambda mx would be equal to sigma bn lambda n c sine of lambda nx sine of lambda mx. The next step again would be integrating with respect to x from 0 to a. Again, we assume that here integrate and the infinite sum, they commute. We talked about these things a few times. And these integrals all would be 0 if n is not equal to m. The only case where it's non-zero is when n and m are equal, right? And the integral would be equal to a over 2. So bn, which becomes bm here because n and m are equal, becomes equal to the 1 over or 2 over a lambda mc integral from 0 to a g x sine lambda mx dx. So assuming we can compute this integral, we also have bm. So now we have both an and bn for any n. And we only need to plug them into the solution we got here. So here we computed an, now we computed bn. We have both of these things, assuming we can compute those integrals. Sometimes we can just estimate that, or we can sometimes compute them explicitly depending what g and f are. We would have this form for the solution to that equation. So again, let's look at them one more time to make sure it's clear. So this was an or am for every m, integral of f of x times sine of lambda mx. And this was bm. Again, a constant times integral of gx sine of lambda mx. So here, up to this point, we have seen the heat equation on the finite bar, which before midterm we saw that, and after midterm we saw semi-infinite bar and completely infinite bar, and we solved both of them. We did all these things using the product method. Then we studied the wave equation now, and we also solved that again using the product method. Now we are going to see a third example, a third equation called the potential equation. So as you know, we are not really following the book. So if you like to take a look at the book, the wave equation, we talked about sections 3.1 and 3.2. Now we are going to look at the potential equation, which is 4.1. Okay, if there isn't any question, we can continue with the potential equation. Okay, let's start with the potential equation. So suppose we have a region inside R2. So this is R2, this is the plane. And suppose we have a region there which is bounded. Let's say it's a region like this. Let's show this region with R, okay? Suppose we have a function u defined on this region R2, the set of real numbers. Okay, so this function u is a function of x and y. So we can look at the derivative of this function with respect to x. We can look at the derivative of this function with respect to y. We can look at the second derivative of the function with respect to x. We can look at the second derivative of the function with respect to y. And other mixed derivatives. There is an operator defined for these functions called Laplacian. So we have an operator called Laplacian. It means for a function, say we're assuming the function is 2 times differentiable. So suppose we have a function defined on some region inside R2 to R. We can define Laplacian, which we show it by this notation. Sometimes people use also this notation. I prefer this one. We define it to be the second derivative of u with respect to x plus second derivative of u with respect to y. Sometimes in some books you might see it would be defined the negative of what we have here. That's kind of a convention. It's different in different places. Now, I'm interested in this section. We are interested in functions like u, such that at each point in their domain, at any point x and y in the domain in this region R, the Laplacian of u is equal to 0. Okay. Such a function u is called a harmonic function. These functions are very interesting. They appear in many fields in math and other fields, physics and everything else. In geometry, in analysis, they're very interesting and important class of functions. They have some interesting features. One of them is something called Maximo Principle. So suppose again, this is R2 and we have this function u defined on some region to R. At each point, u might be positive, 0 or negative. At each point, we can look at the absolute value of u. And we can see at what point this new function, absolute value of u, is maximized. At which point it has its maximum. And the interesting thing here is that it can never be somewhere inside the region if the function u is harmonic. So if you have a harmonic function, if it's not constant, you can't have the function being maximized inside of this region. So this can't happen. Or also, well, minimum, you can't be minimum. In another sense, in min or max, in both cases, absolute value of u is maximized. That can't happen. Maximum or minimums for u can only happen on the boundary. And this is one of the interesting properties of the harmonic functions. So you know a lot of examples. For example, of course, the constant function is harmonic, but we have more interesting examples of harmonic functions. So let's look at a few interesting examples. One interesting case is that when our region R is a rectangle. This is section 4.2 from the book. So the equation we consider is that the Laplacian of u is equal to 0, where Laplacian is the second derivative with respect to x plus second derivative with respect to y. And it's defined, this function is defined on a rectangle inside R2. So let's say this is here x is 0, here x is equal to a, here y is 0, here y is equal to some b. And then we have this rectangle here. The function u is defined from this rectangle to R, the set of real numbers. So we should have some boundary value condition. The boundary value condition describes what this function u is on these segments. Okay, so I should say what is u of, well, I can, for example, say what u is on this line. Let's start with this one. So in this blue segment, y is 0. So the points on this blue segment are described by x and 0. So let's say that's equal to some f1 of x, where x can change from 0 to a. Then I should describe, it should be as part of the boundary value condition. I should say what u is on this green segment. So let's say u at the point x and y equals to b is given by another given function, f2 of x. Again, x can be anything between 0 and a. Now I should say what is the value of u on this yellow segment. So on this yellow segment, x is equal to 0. And we have variable y. Let's assume that's equal to 0. This is a good assumption to start with. This is the boundary value condition we start with, where y changes from 0 to y. 0 to b, sorry. Also, let's say we have the same boundary value condition on the other segment. Let's say u is also 0 at the point a, and y is equal to 0, where y changes between 0 and b. And there is no initial condition. There's no time, right? It's just a function on a subset of R2. So the goal is to solve these equations and see if we can find some u, or if we can show there exists some u, or something like that. So again, we are going to use some product method. So our approach again is the product method. So we are assuming this u can be written as, sorry, there's no t. It can be written, we are assuming u can be written as a function of x times a function of y. So we show this function with capital X, which is a function of the variable small x, times function of capital Y, which is a function of small y. Okay, let's write down the equation for this thing. So the second derivative of u with respect to x plus second derivative of u with respect to y. Well, when we take derivative with respect to x, that would only applies on the function x. So it would be second derivative of the function x with respect to x times the function y plus the function x times second derivative of the function y with respect to y. And we want that to be equal to 0. Now we can take one of these terms to the other side. Let's take this term to the other side. If we do that, we would get the second derivative of, well, rather than showing the second derivative because it's just, it has one variable, let's show double prime rather than partial derivative, just for simplicity. So we would have x double prime y is equal to minus xy double prime. Now we can separate the variables as we did before. We would have x double prime over x is equal minus y double prime over y. A very similar argument to what we did in hidden wave equation. The first one is a function of x. The second one is a function of y. They can't be equal unless both of them are equal to a constant. Again, this constant can be positive, this can be negative. And similar to the previous cases, if we study each case, we would see, is there any question, Edgardo?
Oh, no, sorry.
Okay.
I thought I was muted.
Okay, it's okay. So just like the previous case, we will learn that it has to be a negative constant. So we can denote that with minus lambda squared. So from this, we would get two equations, right? The second derivative of x plus lambda squared x is equal to 0. The second derivative of y plus, minus lambda squared y is equal to 0. So the equations are similar. The only difference is here in the sign of lambda, the sign behind lambda squared. So let's call them equation number 1 and equation number 2. We have already solved the equation number 1, right? This is the equation that in this course we have solved it many times. We also have a boundary condition. What is the boundary condition? Let's also look at our boundary value conditions here. So u of x and y is equal to x of x times y of y, right? What is u of, let's say, 0 and y? What was the value of that? We assumed it is equal to 0. That was part of boundary value condition. That means x of 0 times y of y is equal to 0. Since we do not want to get a trivial solution constant equal to 0, we should assume x of 0 is equal to 0, not y at every point y, because that would give us a trivial solution everywhere. The other boundary value condition was telling us u at the point a and y is equal to 0. That similarly tells us x at a times y at y is equal to 0. Therefore, again, x at a is equal to 0. So we have this equation here. We have this boundary value condition and this boundary value condition. This is a simple second order equation. We've solved this before. We can see there are, just like the cases we've seen before, there are lambda n for every n, and there's a corresponding solution sign of lambda nx, where lambda n can be n pi over a. We have seen this thing before. Now, the interesting thing is the other equation for y, the equation number 2. For y, we learned that y double squared minus lambda squared y is equal to 0. But for each n, we have one different lambda n. So we have a lot of these equations. To each of them, we can associate its characteristic polynomial, which is m squared minus lambda n squared equals 0. Therefore, m is equal to plus minus lambda n. So these are also the solutions of the characteristic polynomial. So we can write down the solutions to this equation. So if these are the solutions to characteristic equation, y can be a linear combination. I would show it with an, a linear combination of e to the lambda n y plus en e to the minus lambda n y. So this would be yn. So for each n, we get one of these solutions yn. Multiplication of these two things we got, xn of x and yn of y, gives us a solution for the original Laplacian equation, potential equation. It's also sometimes called the Laplacian equation. We denote that by un of x and y. So un would be equal to the x and was sine of lambda nx. Yn was equal to an e to the lambda ny plus bn e to the minus lambda ny. Okay, so this is the, for any n, we have such a thing. In general, U can be a linear combination of these things. Again, there is no need for an extra coefficient Cn here because it would go and absorb into An and Bn. So there is no need for that. The general form would be sine of lambda nx times An e to the lambda n x plus Bn e to the minus lambda n y. And n goes from 1 to infinity. So again, we need to compute this An and this Bn. And again, this is completely similar to what we did before. We should use the initial condition to compute An and to compute Bn. So let's do that. We have a little bit more time left, so we can do that. So sorry, the initial condition is not the correct name. There is no time here. So let me correct what I said. So in order to find An and Bn, we should use the boundary value condition, but the other boundary value condition. So we had a rectangle, right? It has 4 line segments. We have here 4 segments. Each of them gives us 1 boundary value condition. Now, this one and this one, we have already used them to compute x. In order to compute An and Bn, we should use these 2. So these 2 would tell us about An and Bn, the other 2 line segments of our rectangle. Okay, let's write down the other boundary value conditions we have here. So what is the other condition? So one of them is U at x and 0 when y is 0. So it would be here. This is where y is 0. We said suppose this is equal to f1 of x for some given function f1. F1 is given. We want to see what this equation tells us, right? But on the other hand, if I just go back here, I know what u of x and y is. I can just let y to be 0, right? So if y is 0, here I would get 1. Here also I would get 1, right? So I would get something like this. U of x and 0 would be equal to sigma and goes from 1 to infinity sine of lambda nx An plus Bn. That would be one of the conditions. The other boundary value condition we had was u at x and a is equal to f2 of x. Now, this is the boundary value condition at the other segment. So again, we can go back, look at the solution we had, and plug in y equal to a. So what do we get? So let me just say, so this is supposed to be equal to f1 of x. So f of x and a is equal to the sum sine of lambda nx An e to the lambda n a plus Bn e to the minus lambda n a. This is supposed to be equal to f2 of x. So we need to solve these 2 equations to find An and Bn. This might actually prove to be a little bit challenging. There is a slightly easier way to go around this difficulty. And that's by using the sine hyperbolic and cosine hyperbolic. So if we have some equation like this, so in order to go around this problem, we should use sine hyperbolic and cosine hyperbolic. What does that mean? So we had this equation, the second derivative of y minus lambda squared y equals 0. The characteristic polynomial was m squared minus lambda squared, right? So this thing would be equal to 0. Therefore, m would be plus minus lambda. This type, our equation was this type of equation, right? Now, you might, another way of writing down the general, the linearly independent solution of these equations are by sine hyperbolic and cosine hyperbolic. So such equation has two linearly independent solutions. One is cosine hyperbolic lambda y, and the other one is sine hyperbolic lambda y. So the general solution of this equation for any lambda can be written as a cosine hyperbolic y, lambda y, plus b sine hyperbolic lambda y, where a and b are constant, just linear combination of those. However, in our case is slightly different. Lambda depends on n, so it's lambda n. And therefore we get yn, it also depends on n. A and b also depend on n. So this is the form of y which is more useful for us in order to find what these coefficients are. We would continue from here tomorrow. Tomorrow we have class. We continue, we would see using this form of y, we would be able to also compute these coefficients. Hopefully we would continue to see more examples, and potentially we might go to higher dimension. Is there any question? If not, it's a good place to stop. I would be around for a few more minutes. We can chat, and if you have any question, we can discuss.